Welcome to our last recorded lecture here for 1211 this semester. We have finally made it to the end, despite all of the craziness that we've kind of endured here the last couple months. What I want to kind of go over today is taking a look at the final exam, giving some general information about it, as well as maybe some general test taking advice, and going over a little bit of review on a few topics that myself, other faculty, and a couple students have really asked about in terms of kind of seeing quick reviews on them. Because there were topics covered before everything got moved online or were being covered as things got moved online that people wanted to just see a little bit more information on. So first, some general things about the final exam as far as what to expect and kind of some specifics and some details on it. It is going to be 48 questions, all multiple choice, and it is still actually written by the American Chemical Society. So we have kind of handpicked, as in faculty here in North Georgia, we have kind of handpicked the 48 questions we want to use. ACS kind of gave us just a general question bank, and we've developed an exam now that has kind of touches on all the topics and things that we covered and thought were appropriate for our 1211 final exam. It is a little bit shorter than normal. 70 questions is the normal ACS exam that we would have taken had we been still in person like we normally would. So it is a little bit shorter. As a result, the time is going to be adjusted a little bit too. You'll see in a second. The exam itself will be given through D2L. If you haven't taken an exam on D2L yet, it'll be under the quizzes tab. So if you log into D2L, go to your course page for 1211, there'll be a tab across the top that says quizzes. Click that, and you should see an ACS final exam in that tab. Once you open that exam from that quizzes tab, you are going to have 80 minutes to take the test. You'll probably have the entire day of your final exam to take the test, but upon opening the exam, you're only going to have 80 minutes to actually finish the exam itself. And so keep that in mind. 48 questions, 80 minutes. So kind of thinking under a little less than 2 minutes a question, kind of from a time perspective, which is something I'll talk a little bit more about in a minute too, in terms of test taking, strategies, things like that. But I do want people to be kind of aware of that. And in terms of content, it covers a little bit of everything from the semester. There's no one topic that has like 8 questions or something on it. It's pretty evenly divided amongst all the chapters throughout the entire semester. So expect most of the major topics that we've covered this semester are all going to have like 1 to 3 questions maybe on them. And so it is very much a cumulative kind of comprehensive mixture of everything that we have talked about this semester. And it will also be kind of a mixture of kind of hard and easy questions as well. So some questions will be very, very short. It might only take a few seconds to answer and be pretty easy, and some questions will be much harder and might be a calculation that takes like 5 minutes or something. So kind of be aware of that as you're going through. There's going to be a very big mixture in kind of the types of things that are being asked and the types of problems that you're going to encounter. Now, a couple of things that you probably want to do before taking the final exam. First, if you haven't already, you probably, by the time everyone's probably seen this video, you've probably at least gotten an email from your instructor or a post on D2L that's probably going to have an ACS sheet that basically has a periodic table, some equations, some constants, and some conversions for different units. That sheet is expected for everyone to have access to. So go ahead and I would print that sheet out so that you just have it easily available, or just to basically be able to like have it like pulled up like in the window next to where you're taking the quiz. That way you're able to kind of see everything that's on that sheet to help you. And that way you have, like I said, periodic table and all those things that are going to be needed. And you don't have to be like kind of scrambling to find those while taking the test. The other thing, and this is from a functionality standpoint, probably make sure your internet browser is updated. Dedi, who is kind of our coordinator for setting a lot of these things up for our online courses, has told us to try and make sure everyone uses Firefox or Chrome to take this exam. They said Safari may have some issues in terms of loading figures. And so some of the images in particular that are going to be really important for a couple of the questions might not show up properly if you use Safari. So Firefox, or Chrome, make sure they're updated and all the figures and images should load properly and you shouldn't have any problems with that. But just kind of something to keep in mind, good general advice to do before you take the exam. So if you haven't done that in a while and you need to update stuff, try and do that sometime between now and your final exam just to make sure hopefully there won't be any weird problems with that. And the last one, obviously, the last point I want to make is just you want to prepare and study. Right, the exam does touch on everything throughout the whole semester, so that does make it hard to kind of prepare and study. Know like what things do you need to go back and review. And so a good starting point, going back and looking at like old quizzes, old tests, homework assignments, and particularly looking for what are the things that you missed. To look at, all right, what did I miss? why did I miss that? Or do I understand things well enough now that I wouldn't miss that question, hopefully, if I got asked that question again, which is really hopefully the biggest thing about quizzes and tests is that feedback, right? Hopefully you see what you miss and be like, oh, okay, now I understand what I did wrong. And hopefully if you see something similar again in the future, you get that correct the next time. That's really kind of how the learning process is hopefully intended to work. And so that would be a good starting point for me. Like I know when I was a student, that was one of the first things I always did is go back and look at old stuff. Like, what did I miss? And then also looking at what other things were on there, even if I got it right. Like, does this stuff still make sense? Do I still feel comfortable with that material or not? And do I need to just trying to identify what areas do I need to go shore up on a little bit before I get to the final. And if there's some topics you feel like you know absolutely nothing about, that gets a little bit trickier, right? Because there's a limited number of time to study a lot of topics, right? So I would almost encourage, like, if there's topics that you feel okay on, I would probably get really good at those topics and just kind of review those and feel really solid, rather than try and completely teach yourself one topic that is completely foreign that you just don't understand for whatever reason. But the main reason behind that is, like, if there's only going to be a couple of questions or so on each topic, like that, if you spend all your time on one topic, you spend all your time on two questions, but maybe you could have studied like 4 or 5 topics and got really comfortable and now for sure know how to do 8 or 10 questions. And so it's just kind of like a timing thing in that regard, and certain time management to figure out how to properly prepare yourself as best you can. Now, that said, if there are topics that you do feel like you really just don't get, those are things that sometime between now and 12/12, I'd probably advise you to kind of go back and look at and get comfortable with. Now, particularly if it's anything with stoichiometry or solutions, or Lewis structures, and Vesper geometries and polarity, kind of things we're doing here at the end. All of those topics are going to come up all the time in 12/12. And so if you aren't comfortable with those things right now, then the future classes are also going to be difficult with some of those. So even if you don't have them down pat for the final, like, those are, again, just things to keep in mind going forward, because they're things that are important that aren't really ever going to go away. All right, and so we're next going to move into kind of some general tips for taking standardized tests, things that I normally tell my classes ahead of this ACS exam, for those that haven't taken lots of just standardized multiple choice tests before. So first, it is multiple choice. There's no reason to leave anything blank. Wrong answers and blank answers count the same. There are some standardized tests out there that actually will count wrong answers worse than blank answers. This is not one of them. It's just straight multiple choice. You get it right or you get it wrong. That's it. So no reason not to guess on at least everything. All questions are worth the same number of points. So that means that don't let 1 or 2 questions kind of derail things. And I mean a couple things by that. One, that means if you run into a calculation problem that looks like it's pretty lengthy and you're not 100% sure how to do it, don't spend 10 minutes on that one question, right? We just said earlier that, like, with 80 minutes to do 48 questions, from a time standpoint, that's a little less than 2 minutes a question. Like, you don't want to spend 10 minutes on one question, and especially if you're not sure how to do it, it's not worth it. If you know something's going to take a while and you're not certain how to do it correctly, skip it. And if you have time at the end, come back and spend more time on it. Otherwise, come back at the end and just make a guess and move on. It's not that big of a deal for that one question usually. And kind of with that, pace yourself appropriately. Right? Like, keep an eye on time as you're going through. Like, try to make some checkpoints for yourself. Like, for instance, if it's an 80-minute test, like 40 minutes in, you want to be around 24, 25 questions in. Get to like around that halfway point. Just have a kind of an idea of where you are. Ideally, you'd like to be a little bit further, so you have maybe a little bit of time at the end to kind of go back and check and review your answers to make sure you've kind of answered everything and you don't have anything that's blank, and that you've made your best effort or can at least make a decent guess at anything you weren't sure on the first time through. And then the other thing I'd point out with this too, some of the questions are meant to be difficult, right? The goal of standardized tests is basically to spread out students as much as possible, which means that some of the questions are meant to be really easy. They expect almost everyone to get them right. But some of the questions are actually meant to be really hard, where they actually only expect a few people to get them right. So don't panic if you run into a question or two. You're just like, man, I have no idea how to do this, or this is going to take too long, or it's too difficult. As far as, like, I don't know what the right answer is. That's okay. That's going to happen probably in a couple questions in this exam. That's just realistic. But there are some things you can kind of do to try and help make that easier, or at least give yourself better odds of getting those questions right. And that's making good educated guesses. Because almost every question, multiple choice wise, for standardized tests in general, but in particular now for this ACS exam, you can probably narrow down the multiple choice answers to, like, 2 or so, maybe 3, that can possibly make sense, because there's almost always 1 or 2 answers that just don't make sense at all. as long as you understand the topic and kind of some of the general things going on in the problem. So if you can narrow things down, like let's say you're taking the exam, like in normally when we take like a 70 question ACS exam, like the national average is like around 40, which is like a 60 something percent. Like we do curve these. It is like we will probably curve this exam as well. I'm expecting to curve it because I don't expect the average to just immediately be like a normal exam average. It's probably going to be lower than that. And so as a result of that, uh, if there's 10 or 15 questions you're really not sure on, 50% guessing is a lot better than 25% guessing, right? Normally there's four options. If you can narrow it down to like two options that make sense and it has to be one of those two answers, now you can immediately better your odds of like, the questions you didn't know how to do. It's a much higher odds of being able to do better on the test for all those questions you weren't sure on. And that can make a surprisingly big difference, right? Even on a 48 question test, like I said, if there's like 10 questions you have no idea how to do, if you can give yourself 50-50 guessing odds versus like 25%, now you're getting like five right instead of maybe only two or three. Like those two or three questions might be the difference, in a letter grade difference at the end of the semester, or at least for this test. And so some things to kind of think about as you're kind of going through them and trying to do your best in this exam. Like make educated guesses, even if you're not certain from reading the problem. Just try to take some context clues. Like, all right, are there any answers that just absolutely don't make sense that you can rule them out? And just little things like that, they do help a lot with standardized tests. All right, so actual things I'm going to spend some time talking about for review topics. There are a few. It's not a comprehensive full review by any means, right? We have a lot of different topics we've talked about this semester. I can't go over all of them in one little short review session. So I'm going to focus on three in particular. I'm going to take a look at naming because it's something that never really goes away, and it's been a little bit since people have looked at it, and it tends to show up a lot on most ACS exams. There will be probably you can almost always expect a couple questions on just straight naming, but you can almost always expect a few questions that you kind of have to know the naming to be able to do the question. For instance, like a stoichiometry problem that you might have to solve, but it only gives you the name and not the formula. And so you have to know the name and get to the proper formula to get the right molar mass to then do the calculations for your stoichiometry problem potentially. And so things like that, like naming tends to show up more maybe than other topics for that reason. So I'll talk a little bit about it some more. I'll also take a look at some solution stoichiometry. That'll actually be the last thing that I'm going to take a look at. And a little bit with quantum numbers, because I've heard some people, like it's something that for some reason I think always ends up a little bit weird in terms of people taking away the information they really need from them. So we're going to kind of touch on all three of those topics. I'm going to start with naming. It's probably the one I might actually spend the most time on, just so I really want to do a full review over kind of all the different aspects of it, right? So if you're going to name a compound, start, let's say, from like a formula to a name direction. The first thing you have to do is know what kind of compound you're trying to name, right? Not everything follows the same naming conventions, so we have to be able to identify what is it. Is it an ionic compound, which you can usually identify by the fact that it's a metal and a nonmetal, or maybe there's a polyatomic ion involved as well, is your other possibility there for ionic compounds. You can have covalent compounds that are typically always between nonmetals that are making all the bonds. We can have acids, which usually from a formula, you can identify an acid because it has hydrogen as the first element in the formula, and it will usually have hydrogen show up in multiple places in the formula. So in this case, like acetic acid is one of the very few exceptions where hydrogen usually isn't listed first. It's actually listed last to kind of show where it's connected in the acid. And for this particular example, though, you can still see hydrogen's listed in two places in the formula, right? And so when you start seeing things like that, that usually can be an indication as far as like the general structure. And in this case, for acetic acid, also helps point out that we have this little lone hydrogen at the end instead of the beginning for our acid. And the last class of compounds, different sections probably spent different amounts of time on this. Organic compounds. For Gen Chem organic naming, we only have kind of alkanes and alcohols that I ever usually talk about. But you're usually identifying those as compounds that have pretty much only carbons and hydrogens with maybe an oxygen or an OH. And we'll take a look at kind of those naming conventions at the end here as well. So starting off with ionic naming, right? So for all ionic naming, our names are always going to be the ions named separately. So you have your cation or your positively charged ion named first, and then your anion second. Your anion, if it has, or if it is a monatomic, so basically just an individual ion like chlorine being Cl minus, is going to get an "-ide" ending, whereas the cation, nothing changes. The only thing that can sometimes come up for your cation is if you have a transition metal or if you have tin or lead. Usually you need to use Roman numerals to indicate the charge, right? So if we want to give some examples of this, let's say we have FeCl3 as the formula. We want to give what's the name for this compound. Well, we want to name the cation first, which is going to be the metal, right? So in this case, Fe, which is iron. So we'll have iron, which iron is a transition metal, which means we have to indicate its charge with Roman numerals. So to find the charge for your metal, you have to look at what your anion is, right? Our anion is chlorine, or chloride in this case, and we have three of them. Well, chlorine's normally a -1 charge, so with -3 here from our anions, iron must be +3. So when we go to name this, this is going to be iron 3 chloride with that 3 in Roman numerals like that. Another example, if we want to look at BaF2, so for BaF2, if we look at barium is our cation, Ba, it is not a transition metal or tin or lead. So that means barium, it's in group 2 of the periodic table. It's always +2, which means we do not have to do anything to show its charge. If it's in group 2, we know it's always +2, so there's no reason to say anything about it. The fluorine that's here, right? Fluorine is going to get an "ide" ending as well. And so for the name of this, it's just barium fluoride, right? And notice there's no prefixes or things like that. Even though there's two fluorines, there's nothing in the name to show that, because for ionic compounds, it's assumed you always balance the charge to make a neutral compound. So if barium is +2, fluorine's -1 for its ions, so there must be two fluorines. That's why it's BaF2. If we want to go from the other direction, from the name to the formula, right here we have chromium 3 hydroxide. So if we're going to get the formula for this compound, the biggest thing for ionic compounds is remembering to balance charges, right? We have chromium 3. The 3 means that chromium has a +3 charge, and that's it. It doesn't mean anything about subscripts, although there will be a lot of times where you might see that this 3 will match this charge might match the subscript of what comes after it for the anion, but that's not always the case. So don't always be in that habit. Be in the habit of what are the charges of the ions, balance the charges to make things neutral. So in this case, we have chromium 3, so chromium 3 plus, combining with hydroxide, which is OH minus, and has just a -1 charge, which means we are going to need 3 hydroxides in this formula. So it's going to be CrOH all in parentheses 3, right? We have a polyatomic ion that we need 3 of, so the whole polyatomic goes in the parentheses to show that we have 3 of those hydroxides in the formula. All right, take one more example for ionic named formula, magnesium chloride, right? No Roman numerals because magnesium is, if we look in the periodic table, it's in group 2, so it's a +2 charge. We're combining it with chloride, which we said earlier is a -1 charge. So in order to balance charges and make sure the whole thing's neutral, it does have to be MgCl2, right, to balance all the charge over ions. All right, for covalent naming, right? So for covalent, some of the naming is going to look similar, right? We're going to name basically our least electronegative element is going to be named kind of like a cation and go first, which means we don't really do anything to its name. And the second element is going to then have, in our naming, is going to get the "ide" ending. And if you're trying to figure out, like, well, which one gets the "ide" ending, because there's not ions, it's covalent, it's still really just the order the formulas are written in, right? The first element, like kind of what we learned with doing Lewis structures, the first element is usually the least electronegative element. And so that one won't get the "ide" ending. The "ide" ending will go in the element that usually shows up last in the formula. Now, the one big difference from ionic naming is for covalent naming, we do add prefixes. Since there's no charges to balance for ionic naming, we don't know how many of each ion there should be or how many of each element there should be. So for covalent compounds, we actually just give prefixes to indicate the number of each element that's going to be present. Now, there are a couple exceptions with these prefixes. For instance, if you only have one of the first element, you don't put mono as a prefix on that. And additionally, any element that starts with a vowel, really, or an A or an O, we're going to remove the A or the O ending of the prefix. And so we'll see a couple examples that involve these exceptions here. So if we want to start with CF4, carbon and fluorine are both nonmetals, so it's a covalent compound. There's one carbon first, but since it's the first element there, it's not going to get the mono prefix, it's just going to be plain carbon. And then fluorine being the second element will get the "ide" ending, and there's 4 of them, so it does need a tetra prefix, so it'll be carbon tetrafluoride. Right? If we had like P2O5, now we have 2 of the first element, it will get the prefix, which is di, so we'd have diphosphorus. And then for the oxygen, no, we actually take the A, kind of the second exception example that we had up there, we take the A off of the penta, and now it becomes pentoxide. for the second portion of that, for the oxygen portion. Now, the good news, covalent naming, ionic naming, if you're going from the name to the formula, you have to be careful about balancing charges. For covalent, I think it's actually really easy, right? If we have something like tetrasulfur decoxide, well, tetra is a prefix that means 4, so there must be 4 sulfurs. That is a deca prefix for the oxide, but the A gets chopped off again for that kind of exception note we made before. So we have 10 oxygens, so it's just S4O10. That's it. We changed nothing. So whatever the prefixes are in covalent, those are your subscripts, and that is it. You never have to make any changes or balancing or anything weird for those. All right. Apologize for how this kind of showed up there. Sorry. For the acid naming, the biggest thing here, and I apologize for not having these kind of show up with the animations properly. We want to identify the acid type when we're going to name things, right? We have binary acids or oxyacids as our 2 types of acids that we usually encounter. Binary acids simply mean that we have hydrogen and usually one other element. Every now and then, probably the only example I can think of this, you can have a polyatomic that doesn't have oxygen, also gets counted as a binary acid. So like cyanide, CN minus, is a polyatomic that doesn't have oxygen. It's one of the very few. And so if you made an acid out of cyanide, like HCN, we would name it as a binary acid. So it would be like hydrocyanic acid, for instance. That is not something that really ever comes up in 1211, to my knowledge, for like an ACS exam or otherwise. But just something to kind of know and understand, because it might show up a little bit in 1212. Oxyacids, you always have a polyatomic ion that has oxygen. Like that's kind of simple explanation for them. There's some differences now in how we name them. Binary acids are always going to get a hydro prefix and an ic ending. So down here we see an example. We have HBr. So for HBr, it's hydrogen and one other element. It's a binary acid. So we get a hydro prefix and an ic ending. It becomes hydrobromic acid, right? The bromine becomes a bromic for that ending change. For our oxyacids, there's no prefix on them. So that's how we differentiate between these two immediately in the naming process. And additionally, the ending of the acid name depends on the ending of the polyatomic ion. If our polyatomic ends in 8, we'll get an ic ending for our acid name. If the polyatomic ends in ite, we'll get an OUS ending in the acid name. So down here I have an example, H2CO3. So here we're looking, this is a polyatomic ion with oxygen. So right away, this is an oxyacid, so no prefix. And then we have to look at what that polyatomic is. We have CO3, CO3 2 minus is carbonate. So we're going to take the 8 ending, it becomes ic, and it becomes carbonic acid for our name. Like just the 8 becomes ic. No, that's just the direct change. Now, one last example for going the other direction from a name to a formula. So here we're given sulfuric acid, so no prefix, which means that we must have an oxyacid of some sort. We have an ic ending, which means we must have started with an 8. Now, sulfur and phosphorus are a little bit weird for the oxyacids. They get their R's back, right? So even though it's sulfuric, there's no sulfurate, it's just sulfate. So that is what we see then as we put our formula together. It is sulfate is our polyatomic ion. But SO4 has a 2 minus charge for sulfate, which is why we then see 2 hydrogens. So similar to ionic naming, you do balance charges for acids as well. Whatever the charge of your anion is, that's how many protons basically or hydrogens you have to add to balance the charge. And so sulfate minus 2 charge, so that's why it's H2 in that formula. All right, and then the last little naming bits, organic naming. For my class, we talk about alkanes and alcohols. So alkanes only contain carbon and hydrogen, and they all have the formula of like CnH2n plus 2. So this means like CH4 or C2H6, C3H8, C4H10. Those are kind of the common examples that we often see. And they all have a prefix that correlates to the number of carbons in the name and then an ane ending for that alkane. And the nice thing is the prefix that goes to the start before the ane ending, if there's 5 or more carbons, it's the same prefix as covalent naming. So like if it's 5, it's like penta, so it'd be like pentane. It's like pentane, hexane, heptane, octane, etc. For the shorter carbon chains, 1 carbon is methane, 2 is ethane, 3 is propane, 4 is butane. Those are probably the 4 that are going to be the most common. They are fairly common compounds, like methane in particular out of the set comes up a lot at different points in general chemistry. And then for alcohols, there's a lot of these that are probably familiar to you as well. And really, alcohols are just an alkane that has a hydrogen replaced with an OH, or at least simple alcohols that we see for general chemistry are. There are lots of other types of alcohols that are a little more complex than that. We don't worry about those in Gen Chem for right now. The alcohols that we do see are going to be examples of basically an alkane with an OH replacing a hydrogen. So, for instance, CH3OH instead of CH4. We put an OH instead of just the hydrogen for the last hydrogen there. And naming wise, it's going to have the same prefixes we had for alkanes. The only thing we're going to do is change the A and E ending to OL. So instead of methane for CH4, CH3OH is now going to be methanol for the ending. And then C2H5OH would be ethanol. C3H7OH would be propanol, and so on. And if ethanol and propanol are probably terms or names of compounds you're familiar with, right? Isopropanol in particular is rubbing alcohol. Ethanol is the alcohol that's typically found in alcoholic beverages. Methanol is the alcohol that's usually used in a lot of cleaning agents. So those are probably common compounds that you do hear a lot, both in everyday life, and you see them a lot in general chemistry and organic chemistry also. So they are compounds we kind of probably want to be aware of. If we see that name, we want to recognize like what methanol or ethanol is. You might sometimes see these also, like MEOH or ETOH are common abbreviations for methanol and ethanol. You probably will not see any of that on like the final exam, but probably like in 1212, that notation may get used from time to time, and definitely in organic, that notation will show up as well. All right, so hopefully that's kind of a nice quick review on naming. Like I said, you'll see aspects of it kind of show up all the time, both in 1211, 1212, all on to organic and beyond. So the next topic I'm actually going to talk about, I'm a little bit out of order what I had on my slide originally, is going to be quantum numbers. This is something we talked about probably right before kind of everything moved online. So it's probably one of those topics that a lot of people glanced at. Then everything kind of got crazy. People forgot about it a little bit. It showed up on maybe your exam 3. And from what I've gathered from other faculty, myself included, is I think general understanding of the quantum numbers is still a little iffy for a lot of people. So I wanted to talk a little bit more about what they are, what they tell us, what kind of things you want to be aware of from those quantum numbers. So in general, quantum numbers, what they kind of represent for us. Any set of 3 quantum numbers is always used to describe one specific atomic orbital in an atom. And then if we add the 4th quantum number, now instead of talking about orbitals in an atom, we're actually talking about electrons. More often than not, we're probably going to see sets of 3 to talk about orbitals. And one of the other things to keep in mind, your orbitals can only ever have 2 electrons. That actually comes from the last quantum number that we'll talk about. So I'm going to go into a little bit of detail about each quantum number, what it tells us, the kind of different information we can get from it, and what its allowed numerical values are and what those tell us. And then I'll go into kind of some example problems that we can actually see dealing with quantum numbers. So starting out with the first quantum number, the principal quantum number, which is represented by a lowercase n. Information this is going to tell us is going to give us information about the energy level, is probably the most particular. And to a loose extent, it kind of correlates to the row in the periodic table because the numbers and the kind of the possible values you can get for n are going to be whole integers starting at 1. Right? It's like 1, 2, 3, 4, etc. And for our current periodic table, it maxes out at 7. That'd be the biggest n that we can get right now. You can also think of n as kind of a little bit of information in terms of size, right? Because as you go down the periodic table, things get bigger, right? You have more shells of electrons effectively. So another way to think of n is it's almost like a particular shell, like an energy level of electrons. All right, our second quantum number, L. We call it the angular momentum quantum number. There are some textbooks out there that might call it the azimuthal quantum number, but I think at this point, angular momentum quantum number is what you'll usually hear it referred to as. And what L will tell us is it tells us the orbital type or shape, which if you know the orbital type, like the shape then it corresponds to that. So those two kind of go hand in hand with one another. Now, possible values of L range from 0 at the lowest up to a maximum of n minus 1. So L values do depend on the n value. If your n value only equals 2, L can only be 0 or 1. It can't be bigger than that. And this kind of correlates to things we see on the periodic table then. Right? The first row in the periodic table is only 2 elements across because when we're in n equals 1, L can only be 0, which is going to be an s orbital. And we're going to talk about how we know there's only 2 electrons that go in one s orbital and why there's only one s orbital here with the next couple quantum numbers. But some things to keep in mind, these numbers for L actually tell us the orbital type. right? L is 0 means s orbital, L is 1 is a p orbital, 2 is d, and 3 is f. All right, a third quantum number, we call this the magnetic quantum number, m sub L. And what m sub L tells us, it tells us the orientation in space of an orbital, but the other piece that's often overlooked is it also gives us the number of orbital type per energy, or per energy level. And so what I mean by that is like our values for m sub L can range from negative L to positive L, and this will tell us how many of each particular orbital type there are in an energy level. If L is 0 for an s orbital, the only possible range that we can get here for m sub L is just also 0, right? Positive or negative, you can't have positive, negative, 0, so L is just 0, and that's it. So we have one s orbital in every energy level, right? For p orbitals, L is 1. That means if we can go from negative L to L, we would include 0 in that, and so we'd have negative 1, 0, and positive 1. That's 3 possible values of m sub L, which is why there's 3 p orbitals in every energy level. For d, L equals 2, right? And if it ranges from negative L to positive, we'd have negative 2, negative 1, 0, 1, and 2. That's 5 values, so that's why there's 5 d orbitals, and so on. And F will have 7 for the same reasoning. Now, the last quantum number, m sub s, is kind of the last bit that kind of puts a lot of pieces together. Then I'll kind of relate these back to the periodic table some, and we'll take a look at some example questions that can come up. But our magnetic spin quantum number, m sub s, just gives us the electron spin of the electron in particular that we're talking about, right? Because in order for 2 electrons to occupy the same orbital, they do have to have opposite spins. We see that m sub s, and I apologize, that is a typo that I will fix right now to make sure that it is not overly confusing. That should say m sub s. I apologize. Get back down to the bottom there. Sorry for that. M sub s can only be plus 1/2 or minus 1/2. That's it. And so this really just tells us that if our first 3 quantum numbers describe one particular orbital, as soon as we add the 4th quantum number, which is this plus or minus 1/2, that means that each orbital, if we're talking about electrons, can only have 2 electrons in it because there's only 2 possible m sub s values. And something called the Pauli exclusion principle says no 2 electrons in an atom can have the same exact 4 quantum numbers. So like all of this kind of put together, like big takeaways, like what do we take away from this? Any one orbital can only have 2 electrons. And if we're looking at the periodic table, now hopefully more of it makes sense, right? We have the S block of the periodic table that's 2 columns because in each energy level, we set up here for the magnetic quantum number, if L is 0 for an s orbital, that means that m sub L is 0, and there's 2 m sub s values, so that's why there's 2 basically electrons that can go in the s block. And then for the p block, it's 6 spaces across in the periodic table, right? Well, it's 6 spaces because we said for a p orbital, there's 3 possible m sub L values. That means there's 3 p orbitals in each energy level, 2 electrons in each of them means 6 spaces across. The d block is 10, right? Same reasoning, 2 electrons in each of the 5 d orbitals. The f block is 14. Again, 2 electrons in each of the 7 orbitals. And so a lot of these things with the quantum numbers can actually be related back to the periodic table. And again, the more you kind of understand them, the more things kind of make sense about why the periodic table looks a little bit like it does, and things like that. Now, questions that often come up with quantum numbers, some things that people should probably be comfortable answering. So here we have an example question. Which of the following sets of quantum numbers would not be a valid set to describe an electron in an atom? So if we look at these, the first one here, n equals 3, that's fine. Like n just has to be any, like starting at 1, going up, whole numbers. L is 2, L starts at 0, can be a maximum of n minus 1. Well, that seems fine. M sub L here is minus 1. Well, m sub L can range from negative L to positive L. That's in that range. That seems fine. M sub S is 1/2. That also seems fine. So everything as far as how these quantum numbers are related to each other is fine. So this first one should be perfectly fine. It's a valid set of quantum numbers to describe an electron. For the second set, we have n equals 2, which is fine. We have L equals 1, which is perfectly fine if n is 2. Then we have an m sub L of 2. Well, that's kind of a problem, right? M sub L can only be from negative L to positive L. If L is 1, m sub L cannot be 2. So this set is not a valid set of quantum numbers because m sub L does not follow its limitations based on the L value that we have. And so that's kind of the thing about how you want to know like how these quantum numbers are related to be able to kind of identify. If we look at the last example, n is 4, L is 0, m sub L is also 0. Well, L being 0 is fine. If L is 0, M sub L has to be 0, so it's fine. Again, M sub S plus 1/2, also fine again. So it's just this middle one that would be incorrect, right? That would be our answer that we'd be looking for in this particular case. Now, other things we can do kind of with this information, actually, before I even go to the next question, some general things on notation, right? If I was talking about what orbital are these first three quantum numbers describing, right? If n is 3 and L is 2, we said before 2 is a d orbital, n being 3 means it's a 3d orbital, right? L is 1 is a p orbital, n is 2, that means this is a 2p orbital, L of 0 and n of 4, this would be a 4s orbital. So just some other kind of orbital notation review things that we can take a look at as well. Other kinds of questions we want to be able to answer. How many electrons would it take to fill the 3D set of orbitals? Well, the set of 3D orbitals in general, right? D orbitals, L equals 2. There's M sub L's, there's 5 possible M sub L values. So that means there's 5 D orbitals. If each one can have 2 electrons, that should be a total of 10 electrons to fill our D set of orbitals, right? That's something we want to be kind of also kind of cognizant of and be able to figure out like how many electrons to fill a particular set of orbitals, or maybe even an energy level of orbitals, and which one we able to think about, right? For each set of orbitals, how many electrons does it take to fill them? Well, your blocks in the periodic table are a nice clue that you can always look at to also help with that. All right, and then last one, here, give a valid set of 3 quantum numbers for a 4f orbital. And so in this case, if it's a 4f orbital with kind of the notation and naming things that I was just talking about, the 4 in front means that n has to be 4. The f means that L has to be 3. And then your M sub L value can be any of the possible values, right? So M sub L has a bunch of options, anywhere from -3 to 3 as integers, including 0. Any of those are fine. So you can just pick any of the 7, and that would be okay. Right, so hopefully that gives kind of a nice quick overview and review of quantum numbers and kind of their quick applications as well. The last thing I want to take a look at is one good example of solution stoichiometry. And again, like I said, I'm not going to go over super comprehensive things here for everything, but hopefully this example, again, kind of give us some other things with like limiting reagents, percent yields, some stuff with solutions, and all of that kind of tied into one problem here. So here we're asked to calculate the percent yield when 25 milliliters of 1.05 molar aqueous sodium hydroxide are reacted with 40 milliliters of 0.650 molar aqueous aluminum nitrate, and in order to yield 0.428 grams of aluminum hydroxide as a solid. So a lot of information in this problem. The very first thing I would probably note here, you're not given a reaction. Right? So the very first thing I would do is probably write a balanced reaction for this. And so what I'm going to do is I'm going to actually work this out as kind of like a final whiteboard example for the semester here too. So if we're looking here, if we're told we have sodium hydroxide reacting with aluminum nitrate. So we probably want to write a reaction for this. And so that's what I'm going to do to start out with. We're going to write a reaction that is sodium hydroxide, so NaOH, plus aluminum nitrate, which is Al NO3, 3, right? Nitrate's -1, aluminum is +3 in its charge. These are both aqueous. And we're told that we're making aluminum hydroxide. Well, balancing that should be AlOH3 as a solid. I'm actually running myself out of room because I wrote too big here. Plus our other solid, which we are going to make another product here. And if you're looking at this, this is a kind of a classic precipitation reaction, right? My other product would be sodium nitrate. And if you're wondering how am I getting these products? Well, precipitation reactions, right? Aqueous plus aqueous making a solid. We're switching our ion pairs, right? So basically the hydroxide and nitrate switch. But to get your products, balance the charges. That's why it's AlOH3. And it's also why my other product here is going to be NaNO3, which is aqueous because sodium and nitrate, both ions that are always soluble. Now, when I look at this, it's not balanced, right? Because here I have 3 nitrates, over here I only have 1. So I am going to need a 3 coefficient on the sodium nitrate, as well as a 3 coefficient on the sodium hydroxide. So I have 3 sodiums and 3 nitrates on both sides. That'll also now give me 3 hydroxides to make the AlOH3 for my aluminum hydroxide as well. So there's my balanced reaction, right? If you're going to do a stoichiometry problem and you don't have the balanced reaction, first step, write the balanced reaction, always. That'll be something that pops up probably a lot in 1212 as well. So there's our balanced reaction. Now, the next pieces of this, our goal is to find percent yield, right? So if we want to think about how we go about finding percent yield should be our actual divided by the theoretical, right, times 100%. That's just the general way of calculating percent yield. The actual yield is what they gave us in the problem, this 0.428 grams of aluminum hydroxide. So what we need to find is the theoretical yield. Well, in the problem, they give us a bunch more information, right? They have volume and a concentration of sodium hydroxide, volume and a concentration of aluminum nitrate. So we have to find now our theoretical yield based on that information. And so I'm going to slide this over just a fraction more so I can see the concentrations at this point. Oops, that is not what I wanted. Apologize for that. There we go. So for the sodium hydroxide, I have 25 milliliters. We'll just write all the information out here first. And for the aluminum nitrate, I have 40 milliliters of 0.650 molar. So I have amounts of both reactants. Even though this problem doesn't mention anything about limiting reagent, if to do our calculation we need a theoretical yield, one of the things we have to know is what is the limiting reagent, right? Because theoretical yield only comes from the limiting reagent. So this is hopefully give us a good chance to review that a little bit here as well. So then the question becomes, well, how do I figure out the limiting reagent? Well, generally what you need to do is for each reactant, you're going to look at how much product can each reactant make. It is possible you could take the amount of one reactant and compare it to figure out how much reactant of the other would you need and compare and see do you have enough of the other one or do you not. You can find limiting reagent that way. I personally think it's easier just to take both reactants, figure out how much product can they make, and then compare whichever one makes less product. That's your limiting reagent, and the amount of product it makes, if you've already found it, that is the theoretical yield. And so you can kind of do it all kind of at once if you look at it that way. I think that's how a number of us will usually kind of demonstrate these kinds of examples. So to do that then, give myself a little more space down here. I'll start with the sodium hydroxide. So if I have 25 milliliters, remember if I'm going to do stoichiometry, I'm going to need this in liters, right? So I'm going to show that's 25 milliliters now in liters, 0.0250 liters, times, I have this concentration, right? And this is all stoichiometry. And I guess maybe I'm getting ahead of myself. I'm going kind of just why am I starting with this, right? I want to start with this the information I'm given on sodium hydroxide. I want to figure out how much aluminum hydroxide can that make. Well, stoichiometry always has the same 3 steps for any stoichiometry problem like this, where you're trying to figure out like how much product can you make from an amount of reactant or how much other reactant would you need, any kinds of relationships of that sort. Stoichiometry is pretty much always starting amounts. You want to use them in some way to get to the moles of that compound you know about, and then do a mole to mole or stoichiometric ratio to get to moles of the compound you do care about. And then the last step, converting to whatever units you want for that last compound, which in our case would be the grams, apologize for that, of the aluminum hydroxide. So for this then, we have our volume. And what I want to do is, if I'm in units of liters, my goal is to get to moles. So for solutions, I can get to moles by taking a volume in liters times the molarity, right? Because molarity, remember, is moles over liter for units. So I can write that molarity, that 1.05, as 1.05 moles of the sodium hydroxide over 1 liter of my solution. Notice how my units are canceling nicely there. And then I said I was going to have a mole to mole ratio. Well, this is why we had to write this balanced reaction, right? I'm going to make 1 mole of aluminum hydroxide, which is what I care about. So 1 mole of AlOH3 divided by, now I want the moles of the sodium hydroxide in my balanced reaction, right? So that I can cancel the moles of an AOH. And there's 3 moles of sodium hydroxide. And this is the step that I see forgotten all the time that makes people mess up limiting reagent problems, right? It's that mole to mole ratio of things. You can't just compare the moles of the reactants. It's got to be moles of like a product or a common thing to be able to make that comparison. And I'm actually going to go one more step, which is I'm also going to put this into grams of aluminum hydroxide. So multiplying this, it's pretty close to about 78.0 grams per mole for the aluminum hydroxide. Oops, sorry. running myself out of space here, trying to squeeze it all into this page. So 1 mole of the aluminum hydroxide, and the top is just the grams of, again, the aluminum hydroxide. So if I multiply all of this out, I am going to get a mass of aluminum hydroxide here that I'm going to make. And if I remember right, I think it's somewhere in the order, actually I calculated this up above. Oh, that thing's in moles. About 0.715 grams. All right, so that's if I use sodium hydroxide. Now I want to do the same thing for this aluminum nitrate. Right, so for the aluminum nitrate, I can take 0.0400 liters, right? That's the 40 milliliters converted into liters, times its concentration. So 0.650 moles of the aluminum nitrate divided by the 1 liter for it. And now for its mole to mole ratio, it should be 1 mole of the aluminum hydroxide per 1 mole of, aluminum nitrate. So that's a 1-to-1 ratio. And I'm going to multiply by that same 78.0 grams per mole. I apologize for kind of squishing things over here in this corner. Not the neatest here. I do apologize for that. This value, I actually don't think I have sitting immediately in front of me. So I'm actually going to have to calculate this real quick. What would that be? So give me 1 second here. All right, and then what that comes out to, now that I've calculated that, I get about 1.87 grams. And so if I'm comparing these two values, I have 0.7715 and 0.187, or sorry, 1.87. The 0.715 grams is the smaller amount. That means that should be the theoretical yield, right? Once I've made this 0.715 grams of aluminum hydroxide, I can't make any more because all of my sodium hydroxide will be gone. I have enough aluminum nitrate to make much more, but once the sodium hydroxide's gone, I can't make more anyway, so it doesn't matter. So the last part of this problem then is to find that percent yield, right? And we said that percent yield was the actual, which they give us in the problem, which was, if I come back over here, I think it was 0.428 grams. So let me come back here and get that value. Yeah, 0.428 grams. So 0.428 divided by my theoretical yield, 0.715 grams, times 100%, which I believe is right about 59.9% for my percent yield in the reaction. So that would be kind of the full example. We see some solution stoichiometry, right? And in general, stoichiometry is always the same 3 steps. Convert to moles, use a mole-to-mole ratio, do a final conversion, whatever unit we need. So in this case, for solutions, that step of getting to moles is a volume and a concentration. If you started out with masses of sodium hydroxide and aluminum nitrate instead, then you have a mass divided by a molar mass as the first step to get to moles. Mole-to-mole ratio, which is why we always want a balanced reaction, right? So we always want this balanced reaction. And the last step then, in this case, I use the molar mass of what the product, because I want to know how much product we were going to make to get that theoretical yield for the percent yield portion. And so those are the steps they went through to eventually piece their way then to our percent yield, right? And again, just terminology pieces like limiting reagent, it's the reactant that runs out first, which is, since you're given the amounts of all of our reactants, anytime you're given the amounts of all the reactants, you kind of have to go through this, what we call limiting reagent process to an extent. Figure out how much product can you make from each reactant, and whichever one makes less product, that's the theoretical yield, that amount of product, and the reactant that caused that amount to be made is your limiting reagent, the one that will run out first. And so that kind of, I think, covers all of the terminology aspects, kind of to go back and review some stoichiometry, which I think is another one of those things we did kind of, like I said, before everything got crazy and moved online. So it probably feels like a lifetime ago at this point, but some good things to hopefully go back and take a look at. And so if these are topics that still feel a little fuzzy, please, like, I would go back and look at more of those a little bit more, because those, like I said, those are things that will typically pop up for this final. You can expect that I know a lot of other faculty had noted that people kind of struggled with the first times through. But that's all I have for this time, which means it's kind of it for this semester. If anyone does have any final questions for myself or other faculty or things for the final, please feel free to reach out to us. We'll do what we can. Otherwise, best of luck in your final exams. Hopefully, everyone has managed to survive this kind of really wacky, crazy semester. And hopefully, if all things go well, we will eventually see everyone back here in the fall.